Hello, my name is Breuer and I'm a PhD student at the Computational Biology group in the Biomedical Engineering department at the Eindhoven University of Technology. In this video I will discuss a part of the Prometheus project, namely the validation of our ray tracing model approach, which can be used to simulate a spatiotemporal temperature distribution under HIFU. At our group, we have developed a model that can simulate temperature maps consisting of two stages. In the first stage, a ray tracing model calculates the heat production. The model incorporates interference between shear and longitudinal waves and can be used to simulate isotropic fluid and solid materials. In the second stage, a finite element model is used to evaluate the temperature over time by solving the heat equation, with the heat production as a source term. As a first step for validation of the model's ability to simulate fluid materials under HIFU, we have set up an experiment with a quality assurance phantom together with the University Medical Center in Utrecht. Here you can see an MR image of the cylindrical phantom. The phantom contains agar and 2% silica. Underneath is the profound V2 ultrasound transducer, which is embedded in castor oil. And between the oil and the agar sits the mylar membrane, which is very thin and has a negligible effect on the acoustics. 4 sonications were performed on this phantom at different power levels, some with different timings during sonication. The temperature difference was measured with PRFS and calculated over time. For the experiment, we imaged 4 two-dimensional slices, 1 transverse slice and 3 coronal slices. All the slices have an in-plane resolution of 2 mm and a slice thickness of 7 mm. From a 3D MRI image and the log files of the SonarLab device, the image on the right was reconstructed. The transverse slice, the QA phantom, the coronal slices, and the profound SonarLab V2 transducer immersed in castor oil. Let's look at the results of the simulation. Here you can see the slices as they are placed in 3D. With PRFS and simulation side to side. The left image shows an experiment at 40 watt with a focus of 2 mm, where the sonication starts at 20 seconds and ends at 40 seconds. Experiment and simulation are next to each other in their 3D context. You may notice a heating up and cooling down period. Next, let's look at all the slices next to each other for the 40 watt experiment. In the simulation on the top row, the region around the focus is simulated. Now let's zoom in into a region around the focus and look at the time response. These are the graphs of the PRFS and simulation for the same 40 watt experiment still. The gray shading indicates a 95% confidence interval, which is calculated by using the measurement error of the 20-second preheating period. The simulation and experiment match up quite okay for this particular setup. Next are the results for an experiment at a power of 20 watts, twice as low as before. This time the sonication duration is 60 seconds, which resulted in approximately the same peak temperature as the experiment on the previous slide. For this lower power, the results matched again quite well. So in conclusion, the PRFS data and the simulation show a good agreement, which even carries over for low power. However, the experiment provides no experimental validation that the modeling approach also works in solid tissue. Future work will attempt to address this issue. Thank you for watching.